Welcome back to the series. In this chapter, we're diving into some of the most practical and real-world concepts you'll use as a network engineer. We'll start by learning how to detect physical network issues that cause problems like latency, packet loss, or poor performance. Then we'll move into wireless technologies, breaking down how Wi-Fi really works, how access points communicate, and how enterprise wireless networks are designed and managed. Let's get started. Modern computer networks have evolved rapidly to meet the demands of an increasingly connected world. To support this growth, networking vendors such as Cisco now integrate traditional physical infrastructure with wireless, virtualization, and cloud technologies. With the rise of smart devices and wireless connectivity, networks must efficiently handle large numbers of devices while seamlessly transferring data between wired and wireless environments. In this chapter, we will explore common physical network issues, core wireless principles, and methods for transmitting data between devices. You will also learn how to deploy and perform basic configurations on a Cisco wireless LAN controller. Finally, the chapter introduces the fundamentals of virtualization and cloud computing. Here are the topics covered. So we have network switch functions and physical layer issues, wireless fundamentals, Cisco wireless architectures, access point modes, wireless components and management, virtualization basics, and cloud computing technical requirements. Network engineers are responsible not only for configuring devices, but also for diagnosing and resolving performance issues such as latency, packet loss, and connectivity problems. Many of these issues stem from interface misconfigurations or physical layer faults. Switches are critical components in networks of all sizes, from small SOHO environments to large enterprise infrastructures. They act as intermediary devices that connect end systems and control how traffic flows through the network. In an ideal network design, a single end device connects to a single switch port. Each physical switch interface represents a collision domain, meaning traffic sent on that port is isolated from others. Unlike hubs, which place all connected devices in a single collision domain, Layer 2 switches isolate traffic per port, preventing unnecessary collisions. Each switch interface and each router interface is a collision domain. A link between a switch and a router also forms a collision domain. When a device sends a frame to a switch, the switch examines the destination MAC address and forwards the frame only to the appropriate port, improving efficiency and performance. Although switches reduce collisions, physical issues can still occur. Network devices running Cisco IaaS provide detailed interface statistics that help identify physical layer problems. The primary command used is show interfaces interface ID. This command displays interface status, MAC address, bandwidth, delay, reliability, transmit and receive utilization, speed and duplex settings, input output errors, and collision counters. TX load and RX load are displayed as values out of 255. A value of 255-255 indicates full interface saturation. Speed defines the maximum bandwidth of an interface. Modern interfaces typically support 10, 100, 1000 megabits per second, meaning they can also negotiate up to 1 gigabits per second. While interfaces default to auto negotiation, this process can fail, resulting in speed mismatches that cause latency and packet drops. For this reason, it is best practice to manually configure interface speeds. Here's the supported speed settings. You have 10 megabits per second, 100 megabits per second, 1 gigabits per second, and auto. Enable auto negotiation. After configuring speed, always verify using show interfaces status, show interfaces, or show running config interface. Duplex defines how devices transmit and receive data. So we have simplex, one-way communication. Half duplex, that's one device transmits at a time. Collisions are possible. And full duplex, simultaneous transmission and reception. And this is preferred. And the Cisco interfaces support auto, half, and full. Although auto negotiation is default, duplex mismatches can cause severe performance issues, including collisions and retransmissions. Best practice is to statically configure interfaces to full duplex, except when connecting to legacy devices such as hubs. So here's some verification commands. The show interfaces command also reveals physical error counters, including input errors, runts, giants, CRC errors, output errors, collisions, and late collisions. Increasing counters indicate physical layer issues. If interface errors are detected, verify speed and duplex settings on both ends, replace the network cable, move the connection to a different interface, and test for faulty network interface cards if issues persist. Physical faults, misfigured interfaces, or failing hardware can all lead to latency, packet loss, and poor network performance. Unlike wired networks that use electrical or optical signals over copper or fiber, wireless networks transmit data using radio frequency signals. Wireless devices such as access points convert the binary data received from an Ethernet interface into radio signals that wireless clients can interpret. The data itself remains unchanged. It is simply transmitted using a different medium. Wireless signals are not physically contained like wired signals, making them susceptible to limitations such as interference, signal attenuation, and security risks. Because of this, understanding wireless signal behavior and frequency usage is essential. Wireless communication relies on specific radio frequencies. Many RF signals exist around us, including those used by radios, walkie-talkies, and Wi-Fi networks, each operating within defined frequency ranges. Wireless networks primarily operate in two frequency bands, 2.4 GHz and 5 GHz. Choosing the correct band is a critical design decision in enterprise environments, as each has distinct characteristics. Radio signals travel as waves. 5 GHz operates at a higher frequency with shorter wavelengths, providing higher bandwidth and faster data rates, but with shorter range and poorer penetration through walls and solid objects. 2.4 GHz uses longer wavelengths, allowing signals to travel farther and penetrate obstacles more efficiently. However, it supports lower bandwidth and is far more susceptible to interference due to congestion. Both 2.4 and 5 GHz signals degrade when passing through walls, metal, and other obstacles. The main drawback of 2.4 GHz is interference, because many nearby networks share the same band. Overlapping signals can significantly reduce performance. Wireless networks use channels to limit interference within a basic service area. 2.4 GHz has 14 channels, but only 3 non-overlapping channels, 1, 6, and 11. Each channel is approximately 20 to 22 MHz wide, and overlapping channels cause interference and reduced throughput. The 5 GHz band offers a large number of channels, much less interference, and channel bonding, which increases bandwidth. Channel bonding works as follows. This allows significantly higher throughput, making 5 GHz the preferred choice for enterprise networks within many wireless clients. Minimize channel overlap between APs while allowing slight signal overlap to prevent dead zones. Wireless networking standards are managed by the Institute of Electrical and Electronics Engineers under the 802.11 family. Over time, multiple versions of 802.11 have been introduced to improve speed, efficiency, and capacity. Wi-Fi 6 improves performance in high-density environments by allowing an access point to communicate with multiple clients simultaneously, rather than servicing one device at a time. SSID Service Set Identifier, it's the Human Readable Wireless Network name. BSSID, Basic Service Set Identifier, the MAC address of the access point. BSS, a single AP and its associated clients. And ESS, which is Extended Service Set, multiple APs using the same SSID on the same wired network. Access points periodically transmit beacons, advertising their SSID and capabilities. Client devices send probe requests to discover and connect to known networks. In an ESS, users can see one SSID, even though multiple APs exist. Clients associate with a specific AP using its BSS ID and can roam between APs as signal strength changes. Roaming causes a brief interruption while the client reassociates. Wi-Fi 7 isn't covered here because it's still emerging and not part of the CCNA exam scope. This chapter focuses on widely deployed exam-relevant wireless standards. Here's the summary for the wireless. So you got 2.4 GHz, longer range, more interference, lower speeds. 5 GHz, shorter range, less interference, higher speeds. Channels and channel bonding are essential for performance. Wi-Fi 6 improves efficiency in dense environments, and SSID, BSSID, BSS, and ESS define how wireless networks are structured. When designing a wireless network, the primary goal is to provide optimal performance, scalability, and manageability for all users. While purchasing access points is straightforward, selecting the correct wireless architecture is critical, as each model has different strengths and use cases. Cisco wireless deployments typically fall into 3 architectures: autonomous, cloud-based, and split MAC. In an autonomous architecture, each AP is independently managed and assigned its own management IP address. Administrators log into each AP individually to configure and maintain it. The advantages to this are simple deployment and suitable for small networks with few APs. The disadvantages: there's no centralized management, configuration changes must be repeated on every AP, and it has poor scalability. As wireless networks scale, centralized management becomes essential. In a cloud-based architecture, APs are managed through a cloud-hosted controller such as Cisco Meraki. Each AP receives a management IP address and connects to the cloud dashboard, which provides centralized configuration and monitoring, radio frequency interference detection, rogue access point detection, and reporting and analytics. The advantages is single management interface, easy scalability, and minimal on-site infrastructure. Disadvantages: requires internet connectivity and ongoing licensing costs. The split MAC architecture uses a wireless LAN controller and lightweight access points. Controlling data traffic between WLC and APs is carried through a CAPWAT tunnel. So UDP 5246, controller management, UDP 5247, data encapsulation. The WLC centrally manages radio frequency optimization, client authentication, security policies, quality of service, and roaming. LAPs handle radio frequency transmission, MAC operations, and data encryption locally. This architecture allows centralized control while supporting geographically distributed APs without complex switch configurations. Cisco's APs can operate in autonomous or lightweight mode. When managed by a WLC, lightweight APs support multiple operational modes. So you got local, default mode, monitor, passive monitoring for intrusion detection system and location services. Flex Connect allows local traffic switching if the CAPWAP tunnel fails. Sniffer captures traffic for analysis using tools like Wireshark. Rogue Detector identifies rogue APs by correlating wired and wireless MAC addresses. Bridge links multiple networks wirelessly. Flex and Bridge provides redundant wireless mesh connectivity, and SE Connect performs spectrum analysis to detect radio frequency interference sources. So here's the summary. You have autonomous, simple but not scalable, cloud-based, centralized, scalable, cloud-managed, split MAC, enterprise-grade centralized control using WLCs, and AP modes allow Cisco APs to support security, monitoring, bridging, and spectrum analysis. Autonomous AP deployments are suitable for small networks, but as the number of access points increases, centralized management becomes essential. This is where lightweight access points and a Cisco wireless LAN controller are used. LAPs contain minimal local configuration and rely on the WLC for centralized control. A WLC is typically connected to the wired network via a switch, allowing LAPs to discover and register with it automatically. LAPs use a CAPWAP tunnel to communicate with the WLC, enabling support for multiple VLANs without requiring trunk ports on access switches. As a result, APs only need an access port connection. Cisco's WLCs use logical interfaces mapped to physical ports. Understanding these interfaces is important for CCNA. So you got service port, used for out-of-bound management, recovery, and initial boot, connected to a switch access port. Distribution system port carries AP client and management traffic, typically configured as an IEEE 802.1Q trunk. Link aggregation allows multiple ports to function as one logical interface, providing redundancy. Console port, used for local access, recovery, and initial configuration. Redundancy port, used for high availability between controllers, and management interface, handles management traffic such as SSH, SNMP, authentication servers, and controller-to-controller communication. A Cisco WLC is initially configured using a console connection and a setup wizard. High-level setup tasks include clearing existing configurations, that's if it's required, setting hostname and admin credentials, configuring the management interface IP, subnet mask, and default gateway, assigning the management interface to a physical port, configuring DHCP, AP manager IP, and virtual gateway IP, defining mobility, radio frequency group settings, and saving and rebooting the controller. Once configured, the WLC can be accessed through a web browser using HTTP or HTTPS. After the WLC is operational, wireless networks can be centrally configured through the GUI. Key configuration tasks include verifying LAPs are discovered and registered, creating controller interfaces and mapping them to VLANs, creating WLANs, enabling the WLAN and assigning interfaces, configuring wireless security, integrating authentication servers, applying quality of service profiles. For enterprise authentication, the WLC integrates with Radius servers to provide centralized authentication, authorization, and accounting. This removes the need for local user accounts on APs and simplifies user management. Cisco WLCs support quality of service profiles. You have Platinum, Gold, Silver, and Bronze. Quality of service ensures critical applications receive priority over less time-sensitive traffic. Summary: LAPs rely on a WLC for centralized control. CAPWAP enables VLAN support and centralized management. WLC interfaces support management, redundancy, and scalability. WLANs, security, authentication, and quality of service are centrally configured, and this architecture simplifies deployment and improves scalability in enterprise networks. Virtualization enables multiple operating systems to run simultaneously on a single physical machine by abstracting hardware resources such as CPU, memory, storage, and networking. Instead of installing multiple operating systems directly on hardware, virtualization uses a hypervisor to create and manage virtual machines. Host operating system installed directly on physical hardware, and guest operating system installed inside a virtual machine and managed by a hypervisor. Virtualization improves hardware utilization, flexibility, and scalability, and is a foundational technology for modern data centers and cloud computing. A hypervisor is the software layer that creates and manages virtual machines. There are two types of hypervisors. A Type 1 hypervisor is installed directly on the physical hardware, replacing a traditional operating system. Virtual machines have near direct access to hardware resources, making this model highly efficient and suitable for enterprise and data center environments. The advantages: high performance, efficient hardware utilization, and ideal for servers and production workloads. Here's a few examples: VMware, ESXi, Proxmox, and XCP. A Type 2 hypervisor runs on top of an existing host operating system such as Windows, Mac OS, or Linux. Hardware resources are assessed through the host OS, which introduces some overhead. The advantages: easy to install and use, ideal for labs, learning, and desktop virtualization. Disadvantages: lower performance than Type 1 hypervisors. Here's a few examples. So you have VirtualBox, VMware Workstation Pro, VMware Fusion, and Parallels Desktop. Running a single operating system on powerful hardware often leads to server sprawl, where CPU, RAM, and storage are significantly underutilized. Virtualization addresses this problem by allowing multiple VMs to share the same physical resources efficiently. Using a hypervisor, administrators can allocate CPU cores, RAM, and storage per VM, run multiple server roles on one physical machine, and scale workloads without additional hardware. This flexibility makes virtualization essential for modern IT infrastructure and cloud platforms. The key takeaways: virtualization allows multiple OSs to run on one physical system. Hypervisors create and manage virtual machines. Type 1 hypervisors are bare metal and enterprise focused. Type 2 hypervisors run on a host operating system and are lab friendly. And virtualization reduces hardware waste and enables cloud computing. Cloud computing allows organizations to use computing resources hosted in external data centers and accessed over the internet. As cloud adoption increases, the need to maintain on-premises physical servers continues to decline. Maintaining local servers introduces several challenges: ongoing IT management and support requirements, physical space, power and cooling demands, and hardware failure risks that can disrupt services. Cloud computing removes these burdens by shifting infrastructure responsibility to a service provider. Organizations can consume resources on demand from providers such as Microsoft Azure, Amazon Web Services, and Google Cloud Platform. These platforms rely heavily on virtualization and automation to deploy services rapidly. Servers and applications run as virtual machines in the provider's data centers, allowing customers to pay only for the resources they use. Common examples include hosted email platforms like Microsoft 365 and Google Workspace, where organizations pay per user and scale services as needed. The benefits of cloud computing: high availability, access from anywhere with an internet connection, reduced on-premises hardware and maintenance, pay-as-you-use pricing, and easy scalability of services. The drawbacks: limited control over back-end infrastructure, shared responsibility for security, and internet connectivity is required for access. Cisco has adapted its technologies for cloud environments by offering virtual network appliances such as routers, switches, and firewalls that run on hypervisors or cloud platforms. Cisco Cloud and automation technologies can be explored on Cisco DevNet. Cloud services fall into three primary categories: software as a service. Users access applications through a web interface without managing infrastructure or software updates. Examples: Microsoft 365, Google Workspace. The responsibility: provider manages everything except user data and access. Then you have platform as a service, provides deployment platforms and tools without requiring infrastructure management. Examples: AWS, Elastic Beanstalk, Google App Engine, and Azure App Services. Responsibility: provider manages infrastructure, users manages applications. You have infrastructure as a service, offers virtualized computing resources such as VMs, storage, and networking. Examples: Azure, AWS, and GCP. The responsibility: user manages operating systems, applications, and configuration. Here's some cloud deployment models. So private cloud, infrastructure owned and managed by the organization, offering maximum control and security. Public cloud, infrastructure owned by a third-party provider and shared among customers. You got hybrid cloud, combination of private and public cloud, often used for redundancy and scalability. And community cloud, shared infrastructure used by multiple organizations with common requirements. In this chapter, you learned how to identify and troubleshoot physical layer issues, understand wireless principles, frequencies, channels, and SSIDs, compare Cisco wireless architectures and AP modes, deploy and manage a Cisco wireless LAN controller, understand virtualization and its role in cloud computing, and identify cloud service and deployment models. You now have the foundational knowledge required to troubleshoot physical networks, deploy enterprise wireless solutions, and understand how virtualization and cloud technology support modern networking key skills for CCNA. I hope you enjoyed this episode. I'm CyberEd, and I will see you in the next chapter. Peace.